Hello everyone. This is our second session on the process models, and we will be looking into what we did last class, and we will delve a little bit more into the process models, and we will go over the prescriptive models today. So the topics that we will cover today, we will start with the build and fix model, and we will then go to the generic versus prescriptive models, and then we will within the prescriptive models we will see the classic waterfall, iterative waterfall, and then the V model. And we will go over to the incremental process model, under which we will also look into the RAD process model. And then we will look into the evolutionary process model, which will have three types of models, that is the prototyping, spiral, and the concurrent development. And we will take up whatever questions you have. You can keep posting your doubts, and I will try to cover as much as possible. So we have a lot of materials for today. In the early approach, in the earlier days, when people started writing software for the commercial use, they were actually not having any software engineering practice. It was not built up. So what used to happen is that they used to do something known as a build and fix. And in the build and fix, there will be two phases. The first one will be the build phase, and the second one will be the fix phase. And in the build phase, the software engineer will try to understand whatever the client is wanting, and he will make a code, create the software, build it in the executable form, and give it to the client. It will be released. So it is only one step, single step. And then you have the rework or the fix phase, where the client, when he starts using this software, they will find so many things which are not adequate. So they will keep giving rework, ask for rework, and the software developer will again go back, build it. So what will happen? It will go into several iterations of build and fix. As a result, what will happen? The maintenance cost will be very high, and it will be difficult to find the source of deficiency, because so many patches have happened on the software, on the programs. When new changes comes, it will be difficult to find how to do it, and you cannot even sometimes debug it properly. So deficiency, the errors will not be found, and one cannot predict how to manage the project within. There is no timeline, there is no cost, and you cannot say anything about the software quality. In fact, the software quality should be told as a very poor. It is very unpredictable. If the software engineer is good, he will make a very good product. Otherwise, it may be thrown away also. So basically, most of the time it fails miserably, unless it is a very small size project. It's a very small size project which is used for maybe very less number of people. Small size project which is used for very small, less number of people, and then it may just be successful. So what was felt is that this is not a very good method, and as and when the complexity of the software increased and the size of the software increased, the number of users were increased. So what happened is there was something known as a software crisis. This is a very well-known term in software engineering, software crisis. You might get a question like this: what is software crisis? What is software crisis is nothing but the symptoms of inadequacy. It's like a disease. It has some symptoms. Symptoms of what is called as an inadequacy in the software or in the software method of development. So what are those? It could be late delivery, over budget, and whatever is the expectations of the user, it's not met, and it has poor quality. What do you mean by poor quality? That means there are frequent crashes. The software while in operation goes down, and not only that it goes down very frequently, but it also has a high downtime. That means whenever it goes down, the maintenance required to put it up and make it running, that may be very delayed. So the total downtime becomes very high. As a result, the user uses it for a lesser time and it is down for the greater time. Many times it is difficult to alter and debug because it's not properly written, it's not properly designed, and users computing the resources that is used is not used optimally. So there is a suboptimal use of the resources, computing resources. And so why does it happen? This is a very normal question anybody will ask. Because of large problems, processes not defined, so many things, lack of adequate training in software engineering because people do not know how to follow the software engineering practice. And also there is very skill shortage in this particular area of software. There is always a skill shortage because matching the right kind of skill is very difficult. So you have to take people who are less trained and train them very fast. And as a result, their productivity will be low, so improvements cannot be made. So that is why process models are needed. Process models will ensure that the software engineering practices are followed and the software is developed in a proper way. So let's look at what is engineering practice. So if you remember in the last class, last week, we said that engineering normally follows a layered approach where the process was at the base. It's the foundation for any good quality production. This is a common feature in all engineering fields. So software has also followed the same practice of other engineering disciplines. And not only that, the process is the base, the foundation, but also it heavily uses past experience. That means how the previous products are built, how the software engineers did the previous projects, what was their experiences, those things are used. How they are used, they are systematically arranged in particular formats in databases. Their failure, success and failure, both, they are analyzed. As a result, what you will know what is why it failed. You can do an analysis why it failed, and you can try to improve those, remove those things, and also you can have some best practices because success of the project will have some best practices. So you can follow the best practices. There will be some guidelines and many thumb rules will be prescribed. So this is the focus of engineering. So in our software engineering process, these are used very much. And because of this past experiences are there, we can quantify it. It will be quantitative, and also statistical techniques can be used because we have collected the data about the past projects in a quantitative manner. And also we can use some of the theoretical basis. That means some research can be made and some inferences can be taken out. A theoretical basis can be put, and these can be used for monitoring, controlling, and also creating some improvements in the process, in the productivity, in the quality. And there will be trade-off between alternatives. This is another criteria, another characteristics of engineering practice. Always we create alternatives and we try to see the trade-off. What is better? Most of the technical activities, we try to see what are the alternatives way we can solve it. And whenever we think of software engineering practice, it has to be a practical or a pragmatic method. It has to be proactive, not reactive. That means we have to think of it earlier and apply it. And always we have to keep in mind that it has to be cost effective while maintaining the desired quality levels. So what is software process model? We have already seen it in the last class. It's a framework, it's a structure, and it has order of activities. Within it, actions, tasks or task sets. And it defines the work product that it produces. It creates some milestones to check the progress, and it serves as a architecture and provides a roadmap, a guideline kind of thing to follow software engineering methods and practices. And we have also seen the generic process model, which can be used for any project. It's not specific to any particular project. It gives a framework which includes these kind of activities: communication, planning, modeling, construction, and deployment. And these can be always adopted. And then we have also seen that there are some quality systems. We will not go into the detail because we have already seen it last time. CMMI and ISO 9000, which make sure that we are actually following the process that we have defined, and they can measure it across the organization. So now today our main topic is prescriptive process model. When we say prescriptive, which means it is a suggestive or a recommendation. So you can think of what is generic and prescriptive. You can think of like taking vitamins, if you're not really very sick in a particular way, you can say, okay, I'm feeling a little weak, let me take some multivitamin tablets. You can go to a doctor. You need not go to a doctor. You can in fact go to the medical disease. I don't have any specific symptoms. But if you have a specific symptom, then you go to a doctor and say, I have this, and then he gives you a prescription. So prescriptive process models, you can think of like that. You have a project, specific project, which has certain characteristics. And for these characteristics, you are looking for the best process model. And you can take the generic model and you can try to adapt it, but it will be difficult. So why don't you take a prescriptive model? So many people have given prescriptive process models. They are suggestive, subject to particular characteristic, people, work environment, things like that. Initially, you can take a prescriptive model. It defines the architecture in a little more detailed than the generic process model. You take the activities of the generic process to create the steps inside your prescriptive process model and start with, and then you can slowly change it. You can build it, you can modify it. And also these prescriptive process models are popularly known as software development life cycle. This is something which you will learn, which you will hear many times. In fact, in your questions, MCQs, in your job interviews, you will hear this SDLC. What they do basically, they organize the framework activities in a certain order. So that sequence and the order is very important. And then they associate these activities or the process elements with the software engineering actions that you will do. So they tell you in this particular activity, you have to do this kind of software engineering action, this kind of tasks you have to take up. And for that tasks, what is the work product you will produce, how you will do the quality assurance, and how you will do the change control. So all other support activities also are defined in it. And it will also establish a workflow of interrelated process elements. So all these elements will be interrelated, so it will create a workflow. So this is how the waterfall model looks like. This is the first model among the prescriptive models. It's a very old model. As you can see, it is in 1970. That is why we call it classic life cycle or a classical life cycle. It's many times called classical waterfall model. And what it does, it's a prescriptive model. It prescribes a sequential linear approach. So it is linear and sequential, very systematic, the well-defined phases, activities which are very rigid. You cannot change them. It's very rigid, it's well-defined. And the phases move only in one direction. If you see the arrows, they are always in one direction. Very much like a waterfall. If you take some water, it will always fall from a height to the lower height. It cannot go back. So that is why this name waterfall has come. And as you can see, some of the activities are associated. So if you go to the how you use it, this waterfall model it is very theoretical. It has more of academic interest. But when the requirements are well understood and the changes expected to be fairly limited during the development process, then, and also if it is a soft and medium-sized project where you have known technology, good understanding of application domain, and it is a regular project which is similar in nature to previous projects, people have good skills and experiences, then you can still use this classical waterfall model, which is a very old model. But most of the time it is used as a theoretical model, which gives you the insight into the different types of activities in the software engineering. So you can understand the software engineering activities by using this waterfall model. So it is used for training purpose. And the classification of the phases, associated activities serve as the base. It's the basis for the other process models, which are basically derived from the mother, which you can consider the classic waterfall model as the mother of all prescriptive processes. So this is another view where this feasibility, this process models, the activities are more like the engineering activities that you actually do. So it is easier to understand. That is why in many books you will find this kind of thing. And these are arrow. Normally in a classic waterfall, they will have only arrow only to the down. So because it will come here and it will come here and like that. It cannot go back. We'll see in an iterative waterfall how we can go back. So as you can see, there is a feasibility study, which is like your communication. And you will have to establish the communication, then you have analysis, specification. We'll go into this each one subsequently. So what is feasibility? It aims to determine whether the developing software is worthwhile, both financially and technically. You can also determine some operational feasibility constraints and whether it is ethical and all, but most important are the financial and the technical. So what you do in this step is actually you try to create a broad requirement, overall requirement, and from the customer. So this is like a communication between the customer, and you try to determine the input to the system processing. Roughly you determine the outputs, constraints, what is the expected performance, what is the expected behavior of the system. So those things you sit with the customer and you determine all these things, and you create some solution strategy. So you know the scope of the broad scope of the software, what it should do and how it should behave, and you create a solution strategy. For those solution strategies, different solution strategies, You determine you estimate the resources that you need, you determine the cost and the development time, and you try to create a cost benefit analysis and try to see if it is feasible, both in the terms of technical, because what type of technology it will require, and whether high cost, resource constraints, those things, you try to see whether you can satisfy whatever it is, the resources that is required and the technical knowledge that is required. The output of this phase is a feasibility report, and it will roughly have the initial estimate and the rough plan also. Then you go to the requirements. Here you focus on the what of the what characteristic of the software, what you want to develop. So here you will go more into the requirements. You will have more communication with the customer. Try to get the exact requirement, more detail of the requirements. And you will have, when we go to the requirements engineering, we will deal with it in more detail. Currently, what we say, there are two types of activities. One is the gathering, analysis, and negotiation, and then you will have the specification. In the analysis, you will be basically trying to find out what are the services, functionality, constraints, goals. This is a collection. The first one is a collection. Then you will, when you analyze, you will build analysis models to show how the software looks like, what it looks like, what is its behavior. Then this will be resolved. There will be so many problems in it, inconsistency, incompleteness. So you will have to resolve all this by discussing and negotiating with the customer. And not only that, you will also prioritize the requirements, whatever are the requirements they have. So you can say this is a must requirement, this is a nice to have requirement. So like that you can classify it, mandatory, nice to have, things like that. And then you will, at the end of it, you will do the specification. So you will have a formal requirement specification. It is normally called as the SRS, software requirement specification, and validate it with the users. Then you will also, as a result of the this phase, you will also do the estimation, because now you have got a better idea of the requirements. And this will have a planning focus. This estimation will be more detailed, and you will go for the planning. So you will create a schedule and a tracking plan. And you will also define the output of each of the phase, each of the task in the schedule. You will give timeline, and you will also determine the output from this phase. What kind of risk management plan, quality assurance plan, monitoring, how you will monitor, what will be the criteria of monitoring, reporting schedules, how you will report to your manager, how you will report to your clients, other stakeholders, and any other associated plans you will do. So this requirement also follows with a complete planning, and you have to see that your monitoring activities are good enough to manage within the main schedule and the budget, and as well as the quality. Then you will come to the design phase in the waterfall model. So here your focus is on how. So what is the main job here is to transform the requirement specification, that SRS, the models that you have made, and the textual description that you have made, you have defined the requirements, that you have to transform it to a more technology related kind of model, so that it will be easier for the software development team to implement it. So you will start with making some software architecture, where you will make modules, you will define the modules, you will define the module architecture. And there are methods, we will go through it later. And you will, basically it's a system abstraction, and it defines the relationship between the modules of the complete system. And you will heavily deal with the modeling and diagramming. There are many more diagramming and modeling you will have to do to describe the technical working of the system. And there are two approaches which we will see in our design classes: traditional function-oriented approach and object-oriented approach. And the outputs will be architecture, high-level design documents with all the diagramming models. And again, there will be quality review and inspection. Next, we will come to the construction phase, which is your implementation of the design. So in this phase, you will basically convert the design to the code, the source code, whatever is the program that you will have to use. So the program modules which you were designed will now be created in a programming language, and you have to test it as a standalone unit. Then, so that is what we have already discussed. We have to also think of reusability and create some module design, because in the design phase, software design phase, we have created only the architecture and a high level design. So now before a software engineer starts to code, that person will have to see, make a detailed module design with along with reusability. Reusability is important because then you can reduce the effort. So you can create your modules in a reusable manner so that it can be put in a different place also. And you have to also check the design optimality. So those things, so that your code will be optimally produced. It will be efficient. If you make an optimal design and optimal code, it will be efficient when it runs. And you have to also check your unit to be functionally accurate as per the design. It should be complete. Everything should be taken care of. And what if there is any expected performance criteria, then we have to see that. And then we will go into the integration. And in the integration, we will basically look into the user interfaces. And we will test the user interfaces. Program interfaces, calls, data passing, screen flow between the user interface modules. Then also whether the programs are correct. There will be a lot of message flow. If it is object oriented, there will be a lot of message flow. So those things we will have to test in the integration. So we will integrate all the units of program modules and build it and look for the integration. So we'll go into it detail later. And now we are only understanding the concept. And then we will build together once all the integrated paths in the program are tested. Then we will make a single build of the system, and we will look for the validation of the system. So validation test will be carried out, and then we will also do the system test where all the non-functional requirements, performance requirements are also checked. So the behavior, the expectation of the customer will be checked. After thorough system testing, it will be delivered to the customer in the validation in the operational environment. The user will have to validate again in an operational environment, in their own environment, in their own way, not the way our software engineers do it. And these feedback or the defects will be reported to the user, to the project team by the users. And we will have to address it. When we will address it before the maintenance. So by the time this integration, at the end of the integration, when we deploy it, we will take feedback. And if there is any problem, we will have to fix it. So you can also make it into multiple steps and multiple phases in your own project so that it will be more defined. And then it will finally go to the maintenance phase. And when it goes to the maintenance phase in the waterfall model, the final phase, that means the software is being used by the customers, there will be 3 different types of maintenance that is done. One is the corrective maintenance. That means some error has remained in the product even after doing so much of testing and feedback and fixing. So over time, it will be slowly, there are a lot of errors which do not surface. It is difficult to surface. It is in fact totally impossible to make a software which is 100% defect free. So some defects will come up and those have to be corrected. Then perfective maintenance, that means we will try to improve the performance of the system. Initially, maybe our design has got some fault. So we will recreate it. And adaptive maintenance means we will have to keep on doing changes because the software will live for 5 years, 10 years, and the business will change, regulations will change, and the technology environment will change. So we will like to port it to new environment, and therefore we have to continuously adapt the software to all the changes that is happening. So that is why, and each time we do some adaptive maintenance, we may have to again do some corrective and perfective maintenance. So what happens is, if you see the maintenance effort for a software in the whole life of the software is 60%, whereas the development effort is 40%. This is an industry standard. So normally as software engineers, we try to give more focus to the development effort. Development we think, and we can see the limitations of the waterfall. The requirements can be clearly stated at the beginning. That is very much required because it is very rigid. It won't allow you any changes. Once it is started, it will not allow you any changes. And all changes, if it is required by the customer, that has to be taken in the evolution or the maintenance phase. And there is a lot of rigidity. One has to complete a given stage before moving to the next phase. That means it is completely linear sequential. There is no overlap in it. The model implies long delivery time because of its nature of linear sequential. You have to finish one, then go to the other one. It has a very long delivery and the customer normally doesn't like it. So the reality for the customer is totally different, exactly opposite to what we have stated here. The customer will not know what is to be required. He will not be able to tell you. And whatever he says, he will go on changing while you are developing it. So you can't make it rigid. And they will not wait until the product is out to absorb the changes in the maintenance phase. They don't have any patience. They want something to be done very fast, use it. They cannot wait for a long time. And some surprises will come at the end. Project takes more time. Team members will be idle because of the dependency. So on and so forth. And the real life people want small things, iterative and not well defined. They will evolve. So that is why we said waterfall model, the classic waterfall model is a theoretical model. It's not a practical model. And this iterative waterfall model basically is a slight modification of the classic waterfall. And it takes care of the limitations of the waterfall model, classic waterfall model. It provides you a backward path from each phase to the previous phases, which was not there. So it is not a waterfall actually. The water can go back here. That means the sequence can be reversed. The sequence of events, of phases can be reversed. The flow of the phases can be reversed by using this backward path to certain small things, not fully. So that is mainly to take care of minor requirement changes during the development. You cannot do a big change, but small little things you can take care. So whereas classic waterfall model is idealistic, assumes no defect is introduced, also there is no changes. This one takes care of defects, also it changes. So initially we said changes, now we are talking of errors. When you do errors, when you when you take one phase, maybe design phase or requirement analysis phase, it is impossible for human beings, for software engineers or human beings, it's very difficult for them not to error. It is in fact very difficult for the customers also not to error. Anybody who, all the stakeholders. So some defects will happen, some misunderstandings will happen, and errors will come up. And when errors will come up, in classic waterfall model, it will flow to the end. But in an iterative waterfall model, because you have this backward path, we can do a phase containment of error. So we can contain it. What we detect errors in the same phase in which they are produced, or at best as early as possible in the development life cycle. So what it means is that if you have completed the design, if you are unable to find out all the design defects, so at least you determine it in the construction phase. And when you determine it in the construction phase, use the backward path, come back to the design phase, correct it and go back. So that is what it says. Using the backward path, errors can be corrected before you go to the end, to the product delivery. So this is the design example I was telling you. This model is highly used by the teams because of its simplicity, the flexibility it allows over the classic waterfall model, and but again the requirements have to be properly understood. So the usage, it has to be properly understood. It has to be general projects, well understood, known technologies. So those things still remain. So you can see this. This is the structure of the waterfall model. It was only up to here. Only this much we had. And now I have given the feedbacks. So you can go back from anywhere to anywhere. In fact, these arrows are double. You should think of it as double arrows. I just missed it. So when I give you the notes, I will change it. So you can come from here to here. You can come from here to here. You can come from here to here. You cannot go back. Maintenance is outside. Model, that is the V model, is an extension of classical waterfall model. It focuses on validation and verification. Validation is another name for testing. So there are two things in it, two phases, distinct phases: verification phases, validation phases, and they are depicted like a letter V, and that is how the name has come. V model for the linear sequential model, but it is a V model. What is the verification phase? Those phases, those activities which use reviews and inspections. For example, your requirement analysis, system design, architecture design, module design, even the coding, you can go for verification, you can go for reviews, you can go for inspection. So they are verification category of activities. Then you have another set of activities which are validation category. They include all the testing activities. And when we say testing activities, it is not only conducting the testing, but also test planning, designing, and designing means designing the test cases, testing, that conducting the testing, recording the test cases, their effect, and also defect reporting. So testing is well designed, focused on test cases, and though largely sequential, there is an overlap between the V and V, between the two activities, basically because of the planning. So let's take a look at the model diagram. So as I told you, these are all the verification kind of category of activities which go sequentially like this, like a waterfall, and you have coding, and then this one goes up like this. I think these arrows need to be reversed. There's a small mistake here. So from coding, it will go to unit testing, integration testing, system testing, and acceptance testing. And in the middle of it, you have all the design activities which go parallel. So although it is a sequential activity, there is some parallelism. That's why we say it is extension of the linear sequential model, waterfall model, and with the more focus on the verification and the validation. It is a test-driven approach. That is what they call it. It's a test-driven approach. In the V&V model, these are the advantages. Users participate during the development stages because of the planning and designing activities. So users have to be brought in, and they can be easily tailored to suit to specific project situation. A model provides enough assistance. For V&V tools can be integrated. It is seen as a test-driven approach. So wherever you have a critical, mission-critical application, which requires a lot of test, you cannot tolerate any small mistakes. There you have to go for this test-driven approach with strict discipline and rigor. So normally medical systems, aircraft control, space missions, which are very mission critical, you have to go for this kind of models. So now we have completed the prescription models which are linear. So we'll go into the incremental process models where we will look at the concept, and we will also look into the RAD process. So in the incremental development process, the concept is that you don't have a single delivery like in the waterfall and its variations. You can make several deliveries. So you don't have a single project, but you can think of it like a mini project. You divide it into many projects. For each project, you have a delivery. So there are several deliverable increments instead of a single delivery, as in waterfall and V models. Each increment is a part of the complete functionality. So first you build this small functionality, this is A, then you build another functionality which is B around it. So initially this much is available, then when you develop B, more is available. So like that you can keep building increments. And each increment is a operational product. That means each increment is usable by the customer. So when you give an increment, you must make sure that the customer is able to use it. That's why I said it's like a mini project. Each project delivery is over. It is usable by the customer. So that is very important when you create an incremental development model activities. So the process flow activities look something like this. You define a rough requirement initially for the full project scope, and then you divide it into some core modules, and then there are some additional modules. So first increment is often the core product or the basic requirement. That has to be developed first and given to the users. And then you can do some add-on supplementary features which will be taken up subsequently. So this identification, this planning you have to do once you have taken all the requirements, you know the full scope, you have done the analysis of the requirements, you don't need to go to the design. You have to first do this planning of your increments. So once you have done the increment planning, then each increment you can develop by either waterfall model, that is, or a iterative waterfall model or a V model, whatever you want to do, and deliver. Once you deliver, it will be given to the customer. You have to take the feedback, and based on the feedback, you may have to 1 minute, just hold on. Yeah. Sorry for the interruption, just a little bit of my power problem. So once you have what we were discussing, once you have developed it, you give it to the customer will give you feedback. So based on the feedback, when you do your next increment, you can refine, change your requirements. So whatever you have defined here, you can change it, you can do a refinement. Then you have to develop the next iteration for the non-core functionality, whatever is you can prioritize it, take that, and again go back. So this will be repeated. So there will be many increments, and until the whole scope of this project is completed. So subsequent increments are planned for modifications because there are some feedback, and also additional features. So both modifications and additional features will be taken up here. Those will be planned and developed. So initially you will have only the planning for identification of these increments, but each project, each small mini project will be planned more detailedly for that particular increment, and finally it will go to the maintenance phase. And the good thing about this is that you can manage your increments based on the technical risks. So you can sequence them accordingly, depending on the risk of the technical side. And each increment will have to follow you can follow the classic waterfall model, or if you want iterative waterfall, but better you freeze it, because they are small increments, so you do no need to change because you can take the changes in the next increment. So you can follow the classic waterfall model and try to make it very fast with frozen requirements. And subsequent increments can have overlap schedule. So you can start the increment 2 before you have started the increment 1, because you have done some initial planning. So you can start this one. You can do the detailed design of the increment 2 while you are doing the testing and delivery of the increment 1. So that will reduce your time. So you can have some advantage of this incremental method in like that. It is particularly useful when project has to be conducted with less number of software engineers. So you have a large project, but you have less small team. So what do? So you try to divide it into smaller projects, smaller, which each one is called as an increment. And you try to design your increments, plan your increments so that they are based on the customer's priority as well as technical risks. And this kind of concept, incremental concept, is also followed in the agile model, which we will take up in the subsequent week, which is an adaptive process model. Now, what are the advantages? Other advantages than what we have already spoken till now. It's very useful when project has to be conducted with less number of software engineers that we have already spoken. Value to user in terms of business need is the focus, because you are delivering very early. So we are trying to see which one is more important. We deliver it earlier. So the customer gets value, business value. So they can use it and they can get the business value. It also increases the transparency in the development because requirements are prioritized by the user. So, and they know what is being done. It is not that the software team is doing it, but the customer is doing it. So they are transparent. The software team is very transparent. They know what is being done. High priority requirements are included in the early increments. And of course, you have to consider the operational and technical feasibility. Higher customer satisfaction is obtained because of business value. It's a result of the business value we talked of. Lower risks of overall project failure, because if you have any problem that is taken out by the in the feedback sessions, and you can also create a prototype in the early increment, which will help us to elicit the requirements for later increments. So that is one thing you can, we'll look into what is prototype later in the evolutionary methods. So you can modify your incremental method by using a prototype. Increased reliability, higher quality of the product. So as you can see, it has very good characteristics. Then we come to the rapid application development, which is another incremental type of development. It is shortly called as RAD. You may get a lot of questions on this. And it lays importance on the short development life cycle. That's why we call it rapid. Within 60 to 90 days, the construction has to be completed. Design and construction has to be completed. The engineering activities, major engineering activities. It's a variation of the waterfall model, where the development is done by several parallel working teams. Unlike the incremental model which we saw now, it is here there are parallel working teams. So the increments are actually parallel. We'll see the structure. It will be clearer when you see the structure. And the requirement is frozen in the beginning. Like waterfall, the requirement is frozen. It is broken into many increments, and each increment is being done by a team, and all the teams are working together. I mean, in a parallel way at the same time period. That's why we call it parallel working. Each team works on a different functionality, which is at a later point of time, it is integrated to create a fully functional system. It achieves a lot of speed because of the parallel way of working, because we have divided the project into many mini projects, but each mini project is being done at the same time by different teams. So you can think of dividing your class into smaller groups, each one doing one work, and at the end of it you add everything together to a product. So within that semester time you finish it. So it's something like that. So reuse and pre-existing software components, you have to do this. Otherwise you cannot achieve that speed, because 60 to 90 days you have to complete. So if you want to complete in such short time, you have to look for some pre-existing software component and reuse them. And there is a stress on the automated tools to have higher productivity. It can follow it can follow a generic process development. So we'll see the illustration. So here in this illustration, I have shown the structure of a RAD process, which is following the generic process framework. To make it simpler, I have used the generic process framework here. So you have a communication phase activity and a planning phase. Then you fork into many you in the planning you have created your increments or your mini projects, whatever you call it. So and you have assigned one team to each one. So each team is doing the modeling or the design, the requirements modeling, the detailed requirement modeling, as well as the technical modeling, the architecture and the design. So all kinds of modeling, business, data, process, technology, everything. And once this is done, it goes to the construction phase. And there you are actually creating your code, testing it up to the unit level testing. For that particular team, all the testing will be completed. And then you have to integrate for the complete system. So each team's work will come and you will have to integrate it and do a deployment and you will get the feedback. So here you may have to do another system testing before you do the delivery. So this is how this time period is 60 to 90 days. It is switched, it's very compressed. That's why it's called a rapid. So here it is totally parallel. There the increments were overlapped. Here it is totally parallel. This is the requirement. Otherwise it cannot be rapid. So each development team can create fully functional software which can be done by a very less time. That's the major benefit. The drawbacks are quite a lot because it should be you should be able to have a large project which is scalable, which can be divided like that. Requirements must be well understood. Project scope can be modularized into scalable to be scalable in nature. Problematic if system cannot be modularized. If you cannot divide it like that into functionally independent modules, independent units, then you have a problem. Requires sufficient human resource because you have so many teams working parallelly. Unlike the other approach where we were taking small teams, here you need a very large team. And project fails if the developers and customers are not committed to the short time frame. If they start doing some other work, then you have a problem because the time period is very important. And one major problem is that it doesn't take care of technical risks. So we don't have any scope for experimentation. No prototype you can do, no experimentation you can do. So you have to use, so you cannot use any new technology here. You have to reuse something which is done, known technology, known modules you have to use. Heavy reuse you have to do. So the risks are little high in this particular project. Now we come to the evolutionary process models. We will be looking into three kinds of process: prototyping model, spiral model, and concurrent development models. So why do we go to this evolutionary process models? Because we have very complex software. And it is so complex that the business and the product requirement keep changing frequently. The customer is unable to tell you what he wants. So obviously you cannot go for an incremental model, you cannot go for a linear sequential model. Because of the complexity, you cannot break it, you cannot know all these things. So what happens, you use an iterative approach which evolves on its own. That's why we call it evolutionary model. We create a simple product and we keep on modifying it, add more complexity to it, and we understand, we evolve the product. We evolve the product and its requirements, both. Because it is so complex that we don't know what is its requirements. And there are, as we said, there are three well-known evolutionary product models. So we'll go one by one into it. And we'll see what is its characteristic. In the prototype, what we do, what is prototype? First, we have to understand what is prototype. Prototype is a toy implementation of a system. It's like something that we play with. We don't give it to the children, but we, the stakeholders, we actually play with it. That means we use it and we try to understand it. We go through it. we run it many times, it has to be executable. It has to be a working prototype. And when you say it's a prototype, it's a toy. Why we call it a toy? Because it has limited functionality, it has low reliability, and it has inefficient performance. So we are not bothering about the full project scope. We are only talking of small little functionality, which is the most complex part of the project you can think of. And it has very low reliability. And we are not trying to create something which will not fail. We are not looking for quality, neither are we looking for the performance. And in the prototyping process model, recommends to start by building a working prototype. That's why I told you working prototype, which has to be executable, and do actual development based on the feedback. So this prototype is always a throwaway type. You don't use it other than trying to find out what the final system will look like. Because it is complex, so you are using the prototype to define it, to understand it, both from the customer side as well as from the technical team. This approach is very useful when customer can provide you a broad objective, generalized requirements with no detail. So you have to develop the detail, you have to evolve by using the prototype. Actual requirement, you have to evolve it. And the developer is not sure of the efficiency of the algorithm. You don't know how it works. You don't know whether the operating system will support these objectives that they are looking for. You don't know how the human machine interaction, the user interfaces, how it will, whether the human machine interaction components that you have will be supporting the UI that the customer is expecting. And or maybe the developer is not familiar with the new technical environment. So here in the such kind of cases, you have to go for some experimentation. So this prototype, the toy implementation, is actually our way of experimenting how the product will be built. That's why we say it's a toy, we will play with it. So it has certain steps, though although it is a toy, it has to be well-defined stages. So we start with the approximate requirement. Then we plan a limited scope to be prototyped. So we have to identify what is that scope that will be prototyped, what features it will have. Then we carry out a very quick analysis and design. We don't waste too much of time in making it efficient and optimized. Because performance is not our criteria when we build the prototype. And we've built a prototype very soon, very fast, very rapidly. And when we do that, we cannot use the normal method. So we use a several simplification. That means we try to create it inaccurate and inefficient functions, dummy functions. We don't create actual computational algorithms. We create some table lookup. We create some data structures instead of databases. So several simplifications, and in the working prototype is to be given to the customer for evaluation. And the customer actually executes it and finds out what is good and bad about it. And accordingly, you keep on refining the requirements and you build again. Each time you refine the requirement, you build the prototype again and you create it like a cycle until the prototype is approved by the user. So when the prototype is approved by the user, you know, okay, this is what the customer wants. So your basic main problem in the project is solved, in the product is solved, because you have got the approval of the user for the particular requirement in terms of this prototype. Then once it is done, the actual requirement evolves using the prototype. So you use the prototype to create the full system requirements, and then you can use any other method, either an incremental or a waterfall model, to develop the actual system. You discard it. So the evolutionary model is basically the prototyping part up to here. Once the prototype is complete, then you throw it. You use it only for getting your requirements. So this is like a graphical method of showing it. You do the communication, you get rough requirement, you decide what you will do, fix the folks, fix the scopes, limited scope, you make a quick plan, quick design, simple construction, and then you deliver it and get the feedback. So this is how the cycle goes, and it goes in a cycle until it is finally approved. Once it is approved, you can exit it. So your prototyping is complete. Then we come to the spiral model. This is another method of evolutionary model. It's called a spiral because it is structured with several cycles in the form of a spiral. Software is developed in a series of evolutionary releases. Activities flow in a clockwise direction beginning at the center. So you have a center of the spiral. It goes in circles in a clockwise direction. The activities will go in a clockwise direction. Each loop in the spiral is split into sectors denoting the activity types of the cycle. So you can have 5 sectors, 6 sectors, depending on the number of activities you have in the cycle, in that particular loop. You will decide how many sectors. Each sector will have a name that will be associated with that activity name. The earlier cycle, the innermost circles in your spiral can be documents, analysis models, design models, or a prototype. When you come to the outer cycles of the spiral, you will have some version of a software. So you will start giving increments, released software to the user, which the user can operate. The early cycles will not be workable software. They will be deliverables, but they will be more of models, prototypes, and documents. And those will be used to evolve the requirements of the later cycles. It combines the evolutionary nature of the prototyping with the systematic control aspect of the linear sequential. Why? Because every cycle is linear sequential, but it has the evolutionary nature of prototyping. So you can do the prototyping and you can evolve, you can determine in an evolutionary method, you can determine the requirements. A very important nature of the spiral model is risk driven. So one of the sectors in every loop will be risk analysis, risk evaluation, and taking care of the risks. So spiral model is characterized by the risk driven. So whenever you find something being asked about risk driven, you know that it has to be a spiral model. Helps rapid development of increasingly more complete version of the software in each cycle. And most importantly, there is no fixed phases. You don't know how many phases. It doesn't tell you that you have to have 6 phases, 4 phases, 2 phases, 3 phases. It is your option. And also the number of spirals are not fixed. So how do you do it? You can start with the generic model. They advocate that you start with the generic model and then you make your own. So this is an illustration. It is followed the generic model. So each spiral is following a generic model, kind of a generic model, only risk analysis is added. So if you see, this is where it is starting. Customer communication, planning. There's a risk analysis because it's highly risk. We said that it is very much focused. Risk is focused. Then you have the engineering activities or the modeling activities. Then the construction or the implementation activities, and you release it, deploy it, and then when you deploy it, you get the customer evaluation and the feedback. Based on the feedback, then you come to the next spiral. Again, based on the feedback, you communicate with and you plan, you determine the scope, the requirements, and you plan for the next one. So it goes. So here I have written communication planning there, all the sectors. So you can see there are 6 sectors in this particular example. Each is an activity, and each spiral is a one deliverable, one kind of a small mini project for you. So spiral model can be adapted to apply throughout the life cycle, including the maintenance phase. Like in the waterfall model also we said maintenance phase. So here also you can say your outer phase is a maintenance phase. So in this particular example, what they are showing is the last one. The white one is the product maintenance approach, whereas the inner one is a concept development project. So you first determine the concept. Then you go to the new product development. So you have developed it. Then you do some enhancement on it because you keep, this is a very basic requirement you have taken. So you need more features. So you add features, you enhance it until you have exhausted all the scope of the project. Then it goes into the maintenance phase. So you have a maintenance project, you take up a maintenance project. Again, you use all the same activities. This is another view. Here you see instead of 6 segments, there are 4 segments. So you have a quadrant. You have 4 quadrant view of the spiral. So you can say this first one is the identify objectives, identify alternate solution, determine objectives, identify alternate solutions. Then for each solution, you have to analyze and determine the impact of the risk and resolve the risks, decide which solution will be the best one. Then you, for that particular solution, you develop it. That means you do all the engineering activities. You have to do the modeling. You have to, maybe you have to do some more requirement analysis, modeling, design modeling, architecture modeling, module design. Then you have to develop it, the code. Then you have to test it. So once it is over, complete, then you come to this. Then you review the product with the customer. You give it to the customer. Let the customer use it and give you the feedback. And based on the feedback, what you will do, you will plan the next phase. So you will come back here. So you will decide what will be your next increment, next spiral, what scope you will take, what features you will take. So for those features, again, you will have to determine the objectives of those features. For the next loop, what is your objectives and what will be the solutions. So I think you have got a very good idea of all the project models. So we'll see the spiral model pros and cons. Let's focus on the risk. It's called as a meta model because it has the characteristics of all other models. It subsumes many other models. Stepwise approach of waterfall, delivery in increments. So it is an incremental type. It has the, it can include the prototyping. It has the risk reduction mechanism. So it is normally called as a meta model because it's not fully defined. It is defined in a very loose model, in a loose way, and you can design it the way you want. The problem areas is because of because it is so loose. So it is very difficult to convince the customers because everything remains undefined. It is not very controllable. It is number of loops are not fixed, so you cannot make an accurate estimation. So project management, controlling, customer conviction, these are the major problems. Also, another problem is, although it is risk driven, but unless you are able to determine the major risk in the very beginning, you may get some problem, and that will affect the cost schedule and the quality. And the last one in this lecture, concurrent development model. It is a kind of a evolutionary model, but here what you have is, you have it is like having many technical tasks and their states. You can think of something like an operating system. All of you are computer science students. So in operating systems, we have many processes and tasks, and they live together, and they are all in different states. At any point of time, only few processes are active. The other have got different states. They could be idle, they could be waiting for input or resources, or they have gone into some other method. So you know what a operating system, you have understood that. So like that, what we will say, in our project, we have many activities and their individual tasks. And each one is there, existing concurrently, all activities, but they are not always active. They could be in sleep mode sometimes. That means they are waiting, they are not active. So some event has to happen to make it transit from one state to the another state. So you can do activity modeling. The activity modeling will describe the states at a given time, and schematically it will define a network of activities and their states. So you all know what is networks. So you can understand, I will show you an example. Each activity's actions and tasks on the network exist simultaneously with other activities, actions and tasks. It is not that when you finish something, you start another one. No, everything is there at the same time, but they are in different states. So everything is not being worked on at the same time, but they are concurrently existing in different states. Events generated at one point in the process network trigger transition to among other states. That's what we told in a little before. So this is kind of an example. Suppose you take any technical activity, say requirement modeling. So you can think of 8 states. The first state is none. That means it is starting. It is not yet started. Then you can say it is going into under development. Under development. Then while it is under development, it is going to awaiting change. That means it is expecting that some change will happen. So it stops development, waiting for changes to come. So when the changes come, it has to do the revisions. So it is under revision. Once it completes it, then it can go to under review. That means the development is over, either the original one or the revision one, and it is under review. So once the review is completed, it can be baselined. That means you can give a version to it, and then it will go to the done. So activity done means it is complete. Activity none, but anytime from the done also it can go back. So that is the beauty of this particular concurrent development model. So let's look at it. So schematically it will look like this. If this is any activity, it can come to under development, it can go to under review, baseline, otherwise goes to awaiting change, under revision comes. But the beauty is that I was telling you, even if it is done, some change may come. So then again it goes to awaiting change. And again it traverses all this circle. So these activities of different activities will stay concurrently in different states. This is very appropriate. Normally it is not very appropriate for normal software engineering projects. But if you are doing computer system engineering, computer system engineering, which will encompass the software engineering, then it is very appropriate, because you have two different kind of engineering activities. You have a hardware engineering activity, then you have a software engineering activity. So, because system engineering will include both software engineering and the hardware. So the hardware is dependent on the software is dependent on the hardware. So it has to be done together, and it has to be done by two different types of people. The model provides visibility regarding the current state of all activities in a project. So these people can know what the other people have done. So these are some of the examples. Other than the computer system, you can have mobile communication product, laptop, smart camera, vending machines. So these are all systems which needs, where the software is very much dependent on the hardware, and the hardware is also very much dependent. They are kind of embedded into each other. And then at the end of it, you do the integration. So this is kind of a flow diagram, activity flow diagram for the computer system engineering. You have a feasibility study, you can do a requirement analysis, then you have to do the partitioning of how much of the requirement will go into hardware, and how much of the requirement will go into software. So as you know, nowadays, even if you take a mobile communication, if you take a mobile phone, even the small systems like its camera, although it is actually a hardware, but you have 4 cameras, and for each of the camera is being driven by a software. So the capability of the hardware is being increased by the software, by the mix of the images that you get out of the 4 cameras. So that is how I'm just giving you an example. Now you can understand what is system engineering. So these are the cases where you will go for the concurrent project development. Otherwise, you don't have to go. Most of the software engineering projects will not require it. High level problem here, the major problem is the higher level problem here is to decide which tasks have to be solved by software, which ones to be by hardware. Hardware and software often develop in parallel. And because of these things, sometimes you need simulators, because when software is ready, hardware is not ready. So you need hardware simulator. Hardware is ready, software is not ready. So you need a software simulator. Concurrent development model is suitable option during the construction, because you have to know what is happening in each other. Integration and hardware and software followed by final system testing. So we have come to the end. The benefits of the evolutionary model. I'll quickly go through it. Continuous change, budget, timeline, and quality. These 3 things have very conflicting characteristics of software development. If you satisfy one, you cannot satisfy two other, but we have to satisfy all the three. And this time to market, this budget and timeline, this timeline constraint is normally becoming smaller and smaller because the customer wants great speed. They want to compete in the market. So they want software to be ready in very less time so that they can take advantage of the speed and go to the market and take the market lead. So they will defeat their competitors. So when we have the very low timeline, speed is a very greater criteria, then there is a threat to quality because it is very difficult to maintain quality. So that's why I said they are conflicting characteristics. But more and more it is coming like that. Evolutionary models can be seen as a balanced solution to the above problem. So you can deliver something, at the same time you can try to create quality. You can use the evolutionary model in an incremental method, in an incremental delivery. The intent of evolutionary process is to develop high quality. The intent is there, iterative or incremental manner by removing risks. This is very important. Spiral model is most suitable for projects with uncertainty or unknown factors. Remember these things because this will come in your examination. Prototyping is used for new technology or clarifying requirements. So this is a type of evolutionary model. Whenever you have new technology, clarifying requirements, you go for prototyping. And when you have large projects, uncertainty, risk, unknown factors, you go for spiral model. And within a spiral model, one spiral initial parallel could be your prototype. Concurrent product development is only used for mostly suitable for system engineering. Disadvantages: spiral model is, as we have seen, number of iterations vary, number of it is not defined. If estimation methodology mostly cater to sequential related process models, so you don't have a estimation method for the evolutionary approach. Guidelines on the speed of the delivery is not available, so it is very difficult to convince the customer. The customer will want too fast delivery, and the team cannot cope up. The quality will degrade. At the same time, if the team says no, we cannot do it, we will be too slow, then it will not be accepted to the business because the business will get affected. It will not be accepted by the customer. So these are some of the disadvantages, and also it can be misused. The evolutionary model, especially in the prototyping, may be misused because customer will say that okay, I want some changes also. I want to extend the prototype to an actual system. Make small changes and try to make it a full system. And but actually the prototype is not made. It doesn't have efficient design. It doesn't have efficient code. So that is technically not possible. But the customer doesn't insists. They don't understand, and they also want to have a lot of flexibility. That means they want to keep on changing. But if you are going by prototyping, after that the requirements are frozen. So if you want terrible flexibility, then you cannot really cope up. And again, the speed of development. So many times you cannot. It is misused because people expect a lot of unreasonable expectation they have, which creates low quality, and the basic objective is lost. So now we will look into the questions. Um, So I'm now looking into the questions. Uh, as I told you, you have to post your questions. Otherwise, this will not be very interactive. So I don't see any questions related to my lecture. What I can do is you can post this later in the later lectures. The next lecture will be on agile models. So if you have any questions on today's lecture, or in last week's lecture, which I introduced the process, the generic process model, and the CMMI and ISO 9000. Those questions, if you have any doubt, that also you can raise in the next session. But in the next session, we will complete all the process related knowledge. And we will go into, in the fourth week, we will go into some different kind of engineering activity. So I will request all of you to go through the software engineering course as well as these two sessions, online sessions, and keep your questions ready. Thank you all.